Hello everyone, welcome to this video. In this video, we will be talking about adversarial searches, which involves game playing. So, let us get started. So, adversarial searches, they are basically used in multi-agent environment, and to talk about these were the first type of problems which involve multiple agents in the same environment. So basically game playing, since it does not happen between one person, um, it generally happens between two or more people. So hence can term it as a multi-agent environment problem, in which any given agent will need to consider the actions of other agents and how they affect its own welfare. So suppose I have player 1, let's say I have player 1 and I have player 2. So these two players will be playing in a game, and this agent will have to consider the actions of the player 2 agent, uh, and also consider how it will affect its own welfare. And they can also produce various contingencies due to unpredictability of the actions of other agent. So it is very much unpredictable because we can predict our own actions, but we will not be able to predict what the opponent, or we will not be able to understand or identify what the opponent is going to play. The next one is that it is involving a very competitive environment. So competitive environment, in it means that it will have a certain sort of competition between the agents which are working in that environment, and here the agents goals are in conflict. Okay, so we will consider the goals of each other which are basically in conflict. That means they do not match with each other. Suppose player 2, its motive is to go in direction 1, or in a way that it will win the game. Player 2 will have an intention which is conflicting to the player 1's intention. That means the goal of player 2 would be somehow trying to minimize the chances of player 1 being winning the game. It was first taken up in 1950 by artificial intelligence domain, and the first game to be developed was chess using this particular search strategy. That means the adversarial searches. So here we will not talk about the modern games like PUBG or um, let's say other such games which are already there. Okay, we will be talking about some very basic problems, not advanced problems like PUBG or Call of Duty or any such other problems. We will be talking about very basic problems like chess, tic-tac-toe, in which the very basic principles of AI has been used. Now, talking about games, whenever we are talking about games, so if we are considering the concept of games, in one part we might have perfect information about the environment, and as well as other associated parameters, and we call it as a deterministic, um, or a deterministic, we call it as a environment which is where we can identify or determine the various consequences. Okay, the second one is we might have imperfect information. That means we do not have, either we might have partial or we might have no information regarding the environment and the players. Now when we are talking about A, which is deterministic, so deterministic essentially will also be coherent to, or it will also be correlated to fully observable environment. So we will be knowing everything about that particular environment, in which there will be two agents whose actions must alternate. Always remember that player 1 and player 2, both their actions are not same. It will be different, and in which we will be associating certain utility values. Now we will also talk about utility. So utility values at the end of the game, and they are always equal and opposite. Whenever I am talking about utility, they are basically the reward points. Okay, so reward points, and this reward points, basically if P1 is getting reward 1 on winning the game, P2 will have an equivalent or an equal but opposite reward. So it will have a negative one, which is, let's say, -1. Okay, now if the first player wins the game, he will be awarded with +1. If the other player loses the game or he is minimizing the chances of player 1's game, he will be using utility -1. So for example, chess. Okay, so in chess also we use the same condition where we have perfect information. That means we have all the environment related information possible, and we will be associating utility with the players, so that whenever one player is winning or losing the game, they are associated with a utility value. But if one player wins a game of chess, we always associate +1 with it. When the other player necessarily loses the game, we will be associating -1 to it. And if none of them wins, then suppose we are drawing the match, or the match is being drawn, so no one wins and no one loses, we will associate 0 with it. But this situation never occurs, because generally in a simple game like chess or tic-tac-toe, there is always one player who will be winning. Similarly, talking about the imperfect information or imperfect scenario, we have various card games. So perfect information, we can consider chess. Now we have various card games in the second category of games. Okay, and here the bridge is basically one of those card games where the information is partial, because all the cards are generally not visible to the player. We do not have all the entire information. In chess we can actually look around at the environment, but in cards we do not have information about what are the cards which are visible to each player. Now we will move ahead with the next important concept, which is related to game. That means the optimal decision in games. So optimal decision in games. So basically this optimal decision in games, it will have a very key role in discussing today's topic, because we will be discussing two important algorithms which are related to adversarial searches or game playing, which is Minimax algorithm and alpha beta pruning. And for that we have to understand that there are certain terminologies which are associated with the search problem of a with the game, or when we represent a game as a search problem. So let us consider, so we will be considering games with two players, with two players. So when we are doing that, essentially the first player we call it to be a max player, and the second player we call it to be a min player. So we will look into this max player and min player when we will be doing this algorithm. But first we have to understand that this max always moves first. That means he is the first player to start the game, and they take turns in moving until the game is over. That means the first move will be by max, move will be by max, the second move will be by min, again the third move will be by max. So alternatively they will be playing against each other until and unless the game is over. So once the game is over, we can actually identify who has won and who has lost the game, depending on the utility values associated with the player. Now a game can be formally written as, or can be formally defined as a kind of search problem, as a search problem. Why it is considered as a search problem? Because ultimately we are searching for what? We are searching for a solution, or we are searching for a state in which the player wins the game. Hence, we can always represent it in a well-defined formula or a well-defined format. So, which will have the initial state. Now, initial state is basically that state which includes the board position and identifies the player to move. So, it will be identifying the player and the board position. So, what will be the board position, or what current state is the board in? So, here they are identified. These two things are identified, because it might be so that we want to begin the game with the min player, but generally Max always makes the first move. But we might also have an option that we might start the game with the min player. Then we will have the successor function. Successor function, as we already know, they are basically, or it is basically a function which returns a list of, so this list will be returned, which will have move and state as the list members, and this is basically a pair which indicates a legal move and the resulting state. So state here basically pertains to the resulting state. Number 3 is the terminal test. So terminal test basically determines when the game is over. So this is like a goal and goal test, but not exactly a goal test, and it determines when the game will be over. And when the game has ended, that state is called the terminal state. The last point that we have to remember while representing a game as a search problem is the utility function. So what this utility function is done represents is, we have already done objective function. So utility function is nothing but an objective function or a payoff function, and this is associated for the terminal states. So whenever a game is ended, that particular state we already call it as a terminal state. And if we are associating a numeric value, if we are associating a numeric value with the terminal state, so let's say terminal state, we will consider that we have associated a utility function, so, or utility value. So suppose in chess, what happens is, whenever a player wins a game, we associate the utility value as 1. If he loses it, we associate as -1. And if it is drawn, that means no one wins and no one loses, then we associate 0. This we have already discussed. The next important point that we have to understand is a game tree. So game tree is nothing but the search space. Okay, so it is the search space in which the game will be played, and in which the terminal states would be search for the terminal states would be done. So initial and legal moves for each side defines a game tree. And we also have to make sure that the moves or the states which we have attained, they are basically legal. We cannot have something like, if a max player is playing, the second move will also be by the max player. No, such kind of uh, rules does not exist in a game. Alternatively, or alternately, the player 1 and player 2 will be playing the game, so that they have equal and fair chances of having or playing the game and winning or losing it. Okay, so we will discuss a problem which is known as the tic-tac-toe. So this problem we have already played a lot. So this is having an environment something like this, and it is a fully observable and deterministic environment. So it will have this: one player will be placing cross, the other player is basically placing a circle, and alternately player 1 will go on placing cross, and similarly the player two's motive would be to minimize the chances of player one's winning strategy, so that player 1 does not win the game. Okay, So, and similarly, player 1 has that strategy of not letting player 2 win. So this is something like this representation, something like this represents a classical tic-tac-toe problem which we have already been playing since our very childhood. And the possible application in AI here is that we have to build a unbeatable unbeatable game of tic tac toe. So this is basically our objective, or this is basically the primary motive of incorporating AI into the game, or introducing game playing strategy. We have to then create an algorithm for the same and use some metric to determine the best possible move. In order to generate, or in order to experiment with these kind of scenarios, we will be introducing the first type of game playing algorithm, which is Minimax algorithm. So Minimax algorithm will help us to build an unbeatable game of tic-tac-toe. Now there are certain assumptions which are related to the Minimax algorithm, and for that we have to, let me write it down. So first, this is the Minimax algorithm that we will be talking about. So when we are talking about Minimax algorithm, the first thing is that the assumption, basically it is, there are certain assumptions. First of all, it is a backtracking algorithm. That means initially the nodes will be expanded until we reach the utility values associated with the terminal nodes, and then it is backtracked to find out the most suitable path. So it is a backtracking algorithm. Then what we have is, if for a perfect game playing strategy, if we want to use a perfect game playing strategy, what we will do is either win we have to either win the game, or we have to draw it. We should not be allowing the opponent to win the game. Either win the game or draw it. And the third assumption is that if another perfect player plays, if player 2 is perfect, that means it is successful in reducing our chances of winning, then I will draw the game. So this should be our primary assumption. And the fourth one is that if player 1 wins, we will associate plus 10 as the utility value. If loses, we will associate minus 10. And if we are drawing the game, then we will simply associate 0 here. Okay, now talking about the Minimax algorithm, first we have to look at a very simple representation of the Minimax algorithm. So suppose, let me draw a tree first, okay, so that later on when we implement this in a tic-tac-toe problem, it becomes easier for us to identify which is the best possible move. Okay, suppose I have a tree here, something like this: A, B, C, D, E, F, G. So this is the tree which we have, and after this we have certain utility values which are associated in the form of these triangles at the terminal nodes. So these utility values will actually tell us what is the chances of winning of that particular node or in that particular direction. So we have utility values as -1, 5, -2, -1, then we have 3, 1, then -4 and 5. So suppose the game is started by max, the game is started by Max. So what does it say? It is basically a backtracking algorithm. That means the algorithm first will propagate to the lowest or the last the terminal nodes, and then it will backtrack in order to find out which is the most suitable option which Max can adopt. Okay, so as already mentioned, they will be playing alternately. So min move is here, again Max will play here. Okay, so now in order to find out the maximum value, as already said, that the best move strategy used will be Max will always try to maximize its utility and min will always try to minimize the utility. That means Max, whatever Max is playing, it will always try to take the maximum value from utility. So here in this level, what is the value D will have? 5 is greater than -1. So by virtue of Max's operation, 5 will come here. Again similarly, here -1 will come, here 1 will come, and here -4 will come. Now min will play, which is the opponent. So before min is playing, we will identify in which direction Max should move. So Max should move in this particular node, it should move towards this direction, here again this direction, here in this direction, and here in this direction. So if Max chooses this particular direction, then definitely Max will win with a utility value of 5 for this node, and here as -1, here as 1, and here as, sorry, here it should have been 5, and here it should have been 3. So because it is playing the maximum value, so 3 and 5. So since we are taking the maximum value of this, so here it will win with a utility value of 5, here it will win with a utility value of 3, here with -1, and here with 5. But this is just one possible option. Now the chance min will get chance to play. So min, what it will try to do, it will try to reduce the chances of Max's winning. So how can min reduce the chances of Max's winning and increase its own chances? By reducing the utility value of Max. So whenever Max has got 5, -1, 3, and 5 here, so here it will try to minimize the utility values in its own step so that Max does not win. So what will be the value? -1 will be the value here, and here 3 will be the value. And out of this, again next chance will be Max's. So Max will take 3. That means the move or the search will take place in this particular direction. Okay. So basically, if this particular direction is followed, which is A, C, and F, or A, C, and G, okay, using the utility value as 5 and 3 respectively, so there is a chance that, so if Max is adopting this particular route, there is a sure short possibility that Max would win the game with a utility value of 3. Okay, but min is playing its best by trying to reducing the values in the intermediate step. However, in the final step, this was not possible. Okay, now let us move to the initial tic-tac-toe problem that we have been discussing. So here what happens is that we said that we will associate +10 for winning, -10 for losing, and if it is draw, we will associate 0. So suppose I have a board position something like this. Okay, so x 0, x, x, 0, 0. So from this state, I have to formulate moves which will be helping me to win the game. Okay, so here from this particular point, I have 3 options which I can take. The first option is this position, which will have simply this. Okay, Then what will I, then what I can give, suppose I have to place x here, so what I can give is the next position is basically in the second one. So under this scenario it will not be winning. And then third one is, suppose here we have x x 0 0 0 x and x. Okay, then after this what do I have? I have here as two different options, which again is giving me two choices each. This will not be further expanded because here already the winning move has been achieved, but in these two representations the winning move has not been achieved. So since x played here, this was x's move, so x played here, now it will be y's move. So x we will be representing as player 1 and y will, sorry, 0 we will be representing as player 2. Let us consider x and y here. So y's move will be 0, so x x, so 0 could be placed here, which would help to win the game, and 0 could also be placed here, which will again further go ahead with a different representation for winning. We will see that. Okay, here also similarly we can place the values, and then we can find out if we have achieved the winning move or not. So this is basically y's move. Okay, so this is basically the y's move. And then finally out of this, so this has already a winning move, here we have got a winning move, again in this particular point we have got a winning move. Now we will go ahead with the next one, which is x's move. So x will play now, so I have to place x in such a way that it wins, and I have an option where I can place x directly in the middle one, so it is winning. Here I am getting the winning move. Similarly here again, let me place another x here, so x 0 0. So here also what happens is I will win the game if we follow this particular move. Now here what happens, since it was x's move, here it is y's move, and then here it is x's move again. So what happens is x will win the game in the last step. So when x wins the game, I will associate plus 10 here, and here also plus 10. Now according to the virtue of Minimax algorithm, what we are trying to do is, since we got the utility as 10, okay, so max will take the maximum value, which is 10, and then in this particular point y will be considering the maximum value, okay, for its own move. So what is the maximum value of y? Maximum value of y is minus 10, because if it loses, if max loses, then we associate the utility value of minus 10. So minus 10 is basically the winning value or the utility value of y's win. Okay, so here since y has won, so we will be associating minus 10 here and here also. But this is an intermediate node, so we do not have to worry much about it. Again here we will be having minus 10. Okay, so similarly again if we are moving to the next point where x has the maximum move, so here we will have plus 10, and here we will have minus 10 and minus 10. Why minus 10 and minus 10? Because out of this one will also have minus 10, because it has not won the game. It has neither lost or not won the game, but we have to associate this as minus 10 because um, it is not giving us a plus 10, or it is not helping us to win the game. Okay, so And whenever we are considering these values, we have to understand that the winning point, okay, wherever we are winning the game, we are introducing this -10 and +10 based on the utility value. Okay, in that way we can identify that if we are trying to consider the move initially from this point to this point, then itself we win the game here. That means +10 is introduced here. However, if we choose any other direction, either this or this, we will not be able to win the game immediately, but eventually we can formulate a way out, which is considering this and considering this. Okay, so this is basically how we can sure shot, or how we can convincingly design a particular um, problem with the help of a minimax algorithm, so that we do not have to uh, we do not have to wait until the opponent is playing, or we do not have to depend upon the opponent's game in order to play the in order to win the game. Okay, we can predict the different steps which are associated with it, so that each and every move which is taken by max or min can collectively help us to determine the best possible move in winning that game. Now, there are certain properties which are associated with this minimax algorithm. So, the first property here that we will discuss is uh, it is complete. See, in this particular game, in this particular search tree, we can also use BFS or DFS. Now, when we are using breadth first search, what happens is each of these nodes will be considered in a layer wise manner. Okay, each of these nodes, each of the layers, or each of the levels will be checked, and each of the nodes in each level will be checked. However, that is not the motive of a game. A game always has to be alternatively played between two players. Okay, so here, since both the players would be evaluated, or both the nodes would be evaluated at the same level, so that will not serve the purpose. Hence, we have to make sure that we use minimax approach when we are using, or when we are going for any game playing strategy. First of all, it is complete because it gives us the terminal states, or it helps us to end the game either in one of the three states, either winning the game, losing the game, or drawing the game. It is complete. The second one is it is optimal. It is optimal. We do not have to search for all the nodes. Instead, we can simply go on deciding the best utility, that is the best move with the maximum utility, and the worst move with the minimum utility. And the third one is the time complexity here is also less as compared to other search algorithms, which is big O b to the power d. So this is similar to what we have already done, but it is lesser when it comes when it is compared with other algorithms of game playing, as well as other searching strategies. And the space complexity here is also less, which is, and b here is the branching factor, and d is the depth. So this we have already discussed, so we will not be again discussing this. You can always refer back to the breadth first search in case we do not understand the time complexity. So space complexity here is also reduced because we do not have to search for all the nodes or all the options simultaneously. We simply have to pick up the best possible move for the with maximum utility for the max move, and the lowest possible utility for the minimum move, and proceed accordingly until and unless the game is won. So this is all about the first algorithm, which is Minimax algorithm, we will talk about adversarial search problems or adversarial search problems from the point of alpha beta pruning in my next video. Thank you.